Hi again, everybody. This is our third installment in our kinetics unit here, third video. And today we're going to be talking about integrated rate laws. Last video we talked about what are rate laws and what are the microscopic and macroscopic factors that would affect them and where do they kind of come from in this thing called collision theory. And today we're going to be talking about integrated rate laws. And if integrated is a term that really makes you shudder because either you're taking calculus now and you're not too enthralled by it, or because you haven't taken calculus, don't worry about it. As you can see here, there will not be any calculus in this video. So we'll gloss over that a bit and just give you the information that you really need. So what is a rate law is something we should recap. So a rate law is an equation that relates the rate of a reaction to the concentration of the reactants, right? So usually it was like rate equals K times the reactants. K was the constant there. And our integrated rate law is one that relates the concentration of a reactant to how much time has passed. So you can imagine that might be a useful thing to have as well, to say, well, it's been 15 minutes, how much of my initial reactant is left over? And we'll use that some, but it's also useful. We can use these integrated rate laws to figure out what the rate law is for a reaction as well. So there's a specific integrated rate law that matches up for each reactant order. So 0th, 1st, 2nd, and you could go on from there, 3rd, 4th, 5th. But these are the typical ones that we see. And even still, the 0th order here is a bit uncommon. A 0th order rate law would be one where all of the reactants have an exponent of 0. So in that case, the rate is independent of how much stuff is there, and it would just be equal to the rate constant. You can imagine if I had concentration of A to the 0th power, that would just end up being 1, and so rate is just equal to K, some constant. The integrated rate law for a 0th order reaction looks like this, where the concentration of A, let's just say A is some generic reactant. The concentration of A at some time t, so again, the t is sometimes excluded, sometimes it's included, but the concentration of A is equal to negative kt, so t is time, and k is the same rate constant that we see in the regular rate law, plus the concentration of A initial. So this t and 0 that you see here, the 0 means initially how much did you have, right? So whenever you see a subscript 0, that is indicating that variable is really not a variable. It's how much you started with initially, which would be constant for that experiment. And the t here is just telling you that this is really the variable. So this is the concentration at whatever time you're talking about. If we were to graph, if I wanted to graph this now, again, it kind of looks like a linear graph here, y equals mx plus b, right? Our y here is the concentration of A. Our m, our slope, is this negative kt. And b is the concentration of A initially. And we can see that play out here in this graph. So the concentration of A is on the y-axis, time is on the x-axis. As time goes forward, we end up with less and less concentration of A because it's a reactant and it's getting used up. If I were to graph this, I could get the equation here, and the equation is this y equals mx plus b. And again, we can pull some information out of this graph because of this relationship. So if this is a linear graph, which it is, then the slope m is going to match up to negative k, right? Y is matching up with the concentration, m is equal to negative k. So if I were to just take the negative of this slope, the k here would be 0.043. The b is the initial concentration of A, right? The y-intercept here is the initial concentration of A. So here it's 2.1, so that's just telling me that the initial concentration of A was 2.1. They get a little more complicated as I move on to different reactant orders. Oh, there we go, auto recovery. Let's take a second here. There we go. It gets a little more complicated when I look at different reactant orders, or the higher reactant orders. So here's a rate law for a generic first order reaction. So rate equals K times the concentration of A to some power 1, right, to the power of 1. And the integrated rate law for that would look like this, where I have the ln, the natural log of A, the concentration of A, is equal to negative kT plus the natural log of the concentration of A initially. So it looks pretty similar, it's just we're taking the natural log of this and this, as opposed to just having the concentration. So what I need to graph now is the natural log of concentration for A versus time. And if I graph that, this is what I get. So on the y-axis now I have the ln of the concentration of A, and on the x-axis I still have T. It ends up giving us a linear plot here, and we have y equals this value, mx plus b, and again it matches up. So since this is a linear graph, it must have a linear format, and our y here now is just the ln of the concentration of A. Our b is the ln of the concentration of A initially, right? So this y-intercept here, this 1.32, means the ln of the concentration of A is equal to 1.32. And the slope now is still equal to negative k. So if I want, I can pull out that same information. So the slope is equal to negative k, and b is equal to the ln of the concentration of A initially. One more here, the second order. So the rate law is rate equals k times the concentration of A squared. That would be a second order in A reaction. And the integrated rate law again looks very similar, but a little different. So now we have 1 over the concentration of A and 1 over the concentration of A initially. And now we have a positive k, right? Usually in the past two we had a negative k, so that changes things. So now the graph, when I graph 1 over the concentration of A versus T, that'll give us a positive slope. So 1 over the concentration of A on the y-axis, seconds time on the x-axis, and we get this equation. And again, we can pull out the same information because it's a linear graph, and we get m, the slope, is equal to k, and b is equal to 1 over the concentration of A. Okay? So you might be thinking, okay, great, what's the point? So we can use this information to figure out what is the reaction order and what is the rate law for this reaction using this integrated rate law method. Okay, so let's say we take this reaction, which is the same one we used in our previous video when we were just looking at the initial rate method. So now that we're going to approach the same reaction using a different way to get to the rate law. So if we can run the reaction and monitor the concentration of N2O5 versus time, then we'll get a whole bunch of information. And we can graph the concentration of N2O5 versus time. We can graph in a different chart the ln of concentration of N2O5 versus time and 1 over the concentration of N2O5 versus time. When I do that, depending on the order of N2O5, one of those plots is going to give me a linear graph, and the other two won't. And so looking at that information, I'll be able to figure out what is the order with respect to N2O5. So here's an example. This might be the information that you're given. You're given all these 3 different graphs for the 3 different potential reactant orders that could apply to N2O5, and what's unknown is the rate law. So we can look at these, and clearly, if I've graphed concentration versus time, ln of concentration versus time, and 1 over concentration versus time, and clearly concentration versus time and 1 over concentration versus time did not give me linear plots, right? And you can tell that usually by looking at the r squared value. So if the r squared value is very far from 1, usually, even something like 0.7811, like that's very far away in terms of like how to analyze these r squared values. So we can clearly see that this is not a linear plot. This is not a linear plot. This one's very good, right? The r squared value is exactly equal to 1, and that's because this is kind of fake data that I put together. But this is telling us that the ln of concentration versus time is giving us a linear plot, And that means that it is first order, because remember, the first order integrated rate law related the ln of concentration versus time, and that was a linear equation. So this is the only one that gives us a linear equation. So the reactant order for N2O5 must be first order. Okay, great. So what does that mean? That means that we can pull some information out of the equation here, just like we were saying. So if it's first order, then this is the equation that applies. The ln of concentration equals negative kT plus the ln of concentration initially. And since we have our equation here, we can figure out, let's say, what K is. Okay, so remember we said here the slope is equal to negative K. And so if I rearrange that, K is equal to negative of the slope. And since the slope is already negative, that means our K will end up being a positive value, 0.175. Okay, well that's great, but now what does that 0.175 mean? What are the units that apply there, right? So what units go along with this K? Well, knowing that it's first order actually gives us a lot of information. So since it's first order, here's the reaction. If it's first order, the rate is equal to K times the concentration of N2O5 to the first power, right? And if the rate always has units of molarity over seconds, and we know that this component here is just equal to molarity, then we know what the units for K has to be. The units for K have to be 1 over seconds, because 1 over seconds times molarity will give us molarity over seconds. Okay? So we know the units for K, and now we can just plug that value in for K, and that'll give us our rate law. So by using this integrated rate law method, we figured out that the rate law was first order with respect to N2O5, and we can plug in rate equals K times N2O5, right? So we've got our rate law. Great. So that's just one method, or another method in our toolbox now of figuring out what the rate law is for a reaction. So we can do the initial rate method, where we go in and we measure the initial rate and the concentration of our reactants and see how that changes. Or we can just run one experiment, monitor the concentration versus time, graph those three things, and figure out which one gives us a linear plot. Another thing that's going to be important here is half-life. So half-life is, very a simple concept. Probably what's going through your head is radioactive decay and like nuclear things, right? Because we'll find out later that they are very useful. Half-lives are very much very applicable to nuclear processes. But a half-life is just the length of time it takes for the amount of a substance to decrease by half. So here's an example. We're looking at our same reaction here, N2O5 decomposing. And let's say we started out here at time equals 0 with a concentration of N2O5 of 4 molar. So the half-life is going to be how long does it take for it to drop down to 2 molar. And we can see here that at 2 molar, the time it takes to get there is 4 seconds. And now if we wanted to look at the next half-life, we would say how long does it take for it to go from 2 molar to 1 molar. And we can see here again, that ends up taking another 4 seconds, right? So at 8 seconds, we've gone from 4 molar to 1 molar. So we've gone through 2 half-lives. It's cut in half twice. And we could go even one further to see how long it takes to get to 0.5, and again, that's another 4 seconds. So what's really interesting here is that the amount of time it takes to cut in half each time is the same, right? It's 4, 8, 12. Each time the half-life seems to be 4 seconds. And that's only going to be true. That's only going to be true for a first-order process, okay? So half-life is a really interesting and useful thing we can look at, but it's only useful and interesting, really, for first-order reactions, okay? And I'll explain why that is later, but we're going to only focus on first-order reactions here. So if we look at our first-order integrated rate law, again, that's ln of the concentration of A equals negative kT plus ln of the initial concentration of A. And if we're talking about half-life, the half-life is the point where the final the concentration of A is equal to 1/2 the initial concentration of A. So if we think about that, so we're going to sub in some variables here. So t1/2 is just going to represent t, but specifically the time at which that one half-life has occurred. And so what we can then do is plug in for A 1/2 the initial concentration. Okay, so we're going to plug that in. So this part where we have A, we're going to plug in 1/2 the initial concentration, and we'll find out that's pretty useful, and it can simplify the equation quite a bit. Okay, so I've plugged in now the T we've written as T1/2, meaning the half-life, and we've plugged in for the concentration of A 1/2 the initial concentration of A. Now this gets into a little bit of like how do you manipulate logs, but if I have two things multiplied and I'm taking the natural log of the whole thing, I can split those into being ln of one thing plus ln of the other thing. Okay, so we can do that. Oops, there we go. So now we can look at this as ln of 1/2 plus ln of the initial concentration. And when we do that, you see that the ln of concentration is added on both sides. So now we can actually subtract the ln of concentration of A from both sides and cancel that out. What that leaves us with is the ln of 1/2 equals negative k times the half-life. Now the ln of 1/2, if I rearrange this, because we want to be looking for the half-life, let's say, I end up with the half-life is equal to negative ln1/2 over k. Again, that's the rate constant. And the ln of 1/2, if you plug that into a calculator, you'll get negative 0.693. So if I plug that back in now, the negatives cancel out, and I get this equation. The half-life is equal to 0.693 over k. And again, that's only for a first-order reaction. But what if we don't have exact half-lives? So what if I want to know when we get to about, 25 or let's take a more complicated example. Let's say, 60%. What if I want to know how long does it take to get to 60% of my initial concentration? Well, we can figure that out. It's just a little more complicated of an equation. So here I have the integrated rate law for a first order reaction. And if I subtract the initial concentration from both sides, I get this. So now I've moved it to the other side of the equation. And again, this is one of the rules of logs, or one of the ways you can manipulate them. If I have the ln of something minus the ln of something else, I can just divide those two things and just take the ln of the whole thing. So I can combine those together now, and I get ln the concentration of A over the concentration of A initially is equal to negative kT. Okay? So again, this is the concentration of A at any given point, and this is the concentration of A initially. So if I divide those two, I could get if I were looking for how long would it take to get to 40% of the initial amount of some material, then I could just plug in 0.4 here and use that in this equation. But what that requires is that I know T and K here, right? So I still have two things that might be unknown to me. So we'll see later how to figure that out. So let's take an example that might relate to half-life. So indium-111 is a radioactive isotope. It decays in a first-order process, right? It's key that it's first order. The half-life for this process is 2.805 days. What is the rate constant for the radioactive decay of indium-111? So what's given here? We've got the half-life, and what's unknown is K. And we don't really know much else. But we don't really need much else. If you remember the equation that we have, the half-life is equal to 0.693 over K. So if I just rearrange that, K is equal to 0.693 over the half-life. I plug in the 2.805 days. And what's important here is that my half-life is going to be in terms of whatever, my rate constant is going to have the units of whatever the time units that I used for the half-life. So in this case, I use days. And so you'll see the units here that I end up with are 0.247 1 over days. Okay, usually we're talking about it in terms of 1/seconds, but for these longer processes, sometimes the half-life is in terms of days or years. So you have to make sure you pay attention to keep track of the units. Let's take another example. So chlorine-36 is a radioactive isotope with a half-life of 3.0 times 10 to the fifth years, really long. How many years will it take for the amount of chlorine-36 to decrease to 75%? Well, that's less than a half-life, right? So I can't use that regular half-life equation. But, sorry, I'm getting ahead of myself. What's given is the half-life. We're given the ratio here of the amount of chlorine to the amount of chlorine initially. And we want to know how long, what's t there. So again, we're going to use our other equation here, this equation. And the ln of the ratio will be equal to negative kt. Okay, well, we know that the ratio there is 0.75, right? We want to know how long it'll take to get to 75%. But we still don't know what k is, right? We're solving for t, so we can rearrange this equation to solve for t, but we need to know k in order to figure this out. But again, remember the half-life is given, so we can go back and use our equation to calculate k that we did in our last problem. So if we're given the half-life, we have this equation, we can calculate what k is, right? 0.693 over the half-life. And so here's our half-life. And again, since we used years, the units here are going to be 1/years. So now I have to go back and take the k value that we calculated and plug it in for the k here in this half-life equation. So I've done that, negative 2.3 times 10 to the negative 6th years, or 1/years. And so if I now just solve that equation, I get 1.3 times 10 to the 5th years. So it'll take 1.3 times 10 to the 5th years in order for 75% of that chlorine-36 to get to a point where only 75% of the chlorine-36 is remaining. Okay? So again, half-life is especially useful for first-order reactions, and the reason for that, the reason the other ones are not useful, is because they do depend on how much material is present, right? So the half-life equation doesn't include the concentration of A anywhere in there, right? It's T1/2 equals 0.693 over K. There's no concentration of A involved in there at all. So that's really useful for first-order reactions, but for second-order reactions, 0th-order reactions, and so forth, those half-lives depend on how much stuff is present. So the half-life changes as you use up some of your material. And since it's not a constant value, since the half-life isn't constant, that's not as useful for us. So you'll really only see half-life related to first-order processes. Radioactive decay is first order, which is why oftentimes when we think of half-life, we're talking about radioactive processes. So radioactive decay is usually first order. And so we can use that to figure out how old things are. It's really useful. And you've probably heard about some of these, or at least one of these ways of dating how old things are. So carbon dating. Carbon dating is probably something that you've heard of. It's using the amount of a certain isotope of carbon in a sample to determine how old it is. Carbon-14 is a radioactive isotope of carbon. Remember, the most common isotopes of carbon are 12 and 13. But there is always a trace amount of carbon-14. That's because it's constantly being produced in the upper atmosphere. So the upper atmosphere is constantly getting bombarded with all these different particles and radiation and whatnot. And so carbon-14 is constantly getting created. And that carbon-14 falls down to Earth, where plants absorb it, and then other organisms eat those plants. And so anything that's alive has some trace amount of carbon-14 in it. And that is actually a pretty constant value. You might think like, well, isn't it slowly going to build up? But while carbon-14 is produced in the atmosphere, it's not stable. So it's also constantly decomposing into nitrogen, actually. So carbon-14 decomposes into nitrogen, and it gives off this thing here called a beta particle. again, you don't need to know too much about this. This is more just kind of interesting things about carbon or half lives and why we use them. So don't worry too much if you're focusing on like, well, what's that beta particle? Don't worry about it. But so you're constantly intaking carbon 14 from the plants and animals that you eat, and you're constantly the carbon 14 in you is decomposing at the same time. And what that works out to is that we have a constant amount of carbon 14 in our body in terms of the proportion of carbon in our bodies at all time. And that's true for all living organisms. So the half life of carbon 14 is around 5,700 years. And so if they take some sample of something that was alive, they can determine how old it is based off of how much carbon 14 is left in that sample. So if 0.001% of the carbon in that sample is carbon 14, that gives them some information. Using what we just talked about, you can calculate how old that thing is. Because once you die, obviously you stop picking up carbon 14 from things you eat because you aren't eating anymore. And so at that point, the amount of carbon 14 just slowly depletes in your body. And so if you have a lot of carbon 14 left in that sample, or close to the amount that's in a living sample today, that means that sample is not very old. If very little carbon 14 is left in that sample, that means that the thing is very old. Because carbon 14's half-life is around 5,700 years, and there isn't very much carbon 14 in things to begin with, it's really only reliable up to about 60,000 years. Any older than that, and now there's so little carbon 14 that it's really hard to measure accurately how old the sample is. So oftentimes this is used to measure the age of, let's say, a campfire that they found that they believe is to be, made by some ancient peoples, right? So, something that might have been made by Native Americans or something many years ago. So they can use carbon dating to figure that out. But anything older than that, it's not reliable. So how do we measure the age of things that are really old? So like bad boy over here, Mr. T-Rex, okay? If we want to know how old Mr. T-Rex is, we can't just take one of those bones and measure how much carbon 14 is in there, because it's going to be so little that we can't really measure it. So what we use is uranium dating. Zircon. So we'll get back to uranium in a second, but zircon is a crystalline substance, a solid mineral, and it has this formula, ZrSiO4. So it's got zirconium, silicon, and oxygen. Zircon will incorporate small amounts of uranium when its crystals form, but it will never incorporate any lead at all. So when it forms, it might contain some uranium, but it will not form and incorporate lead in there. So the lead will be excluded. Why is that useful? Well, uranium decays to form lead in nuclear reactions. And those reactions have a very constant, well-known half-life. It's very long. So uranium-238 has a half-life of 4.5 billion years. It's very slow to decay. So how is that useful? So if I look at a sample of zircon, this mineral zircon, depending on how much lead is in there, right? Because lead doesn't get incorporated in when it forms, but it can form if it has some uranium already in there. Well, when the uranium decays, some lead will be left in there. So we can figure out when did that zircon form by looking at how much lead is in that sample. And that'll tell us how many billions of years old something is, or how many, millions of years old even. Okay? So you might think, well, how does that relate to T-Rex here? T-Rex certainly doesn't have any zircon in him. And what they do is they will oftentimes look at sediment layers. So wherever they find the dinosaur bones, they'll look at the sediment below and look for zircon, and look at the sediment above and find more zircon. And based on the age of those two sediment layers, they can determine the range of years ago that this animal must have lived. or died rather. So, this is how they measure the age of things like dinosaurs. This is how they measure the age of like the Earth. So they have an approximate age of the whole Earth, and it's using these uranium dating or uranium dating methods. There's others as well, but these are just some examples. Here's just some random interesting facts. Tyrannosaurus rex lived around 65 million years ago. Stegosaurus lived around 150 million years ago. And they figured this out using things like uranium dating. And so if you think about that, that means that when T-Rex was alive, Stegosaurus had already been extinct for 85 million years. So longer than the T-Rex has currently been extinct for. But in our minds, and right in any like movie you watch, you always see the T-Rex and the Stegosaurus together, right? But they never lived together. The Stegosaurus was extinct for a huge amount of time before the Tyrannosaurus Rex came around. Kind of similar, ancient Rome, right? Again, it's interesting to think about these scales of time. When ancient Rome was at its peak power, the Egyptian Empire had collapsed 1,500 years before. So it's very similar to how we think about the ancient Romans. The ancient Romans were thinking about the ancient Egyptians. And again, we kind of just think of like, well, they're both really old, so they're all kind of nearby. But actually, the Egyptians had been, the Egyptian Empire had collapsed long before Rome became a significant power. Okay, so just to recap, rate laws relate rate to concentration. Integrated rate laws relate concentration to time. Since we've got these different relationships between the different order of reactants and their integrated rate laws, we can use concentration and time data to figure out the order of that reactant, right? And we went through that. Half-life is the length of time it takes for an amount of substance to cut in half. And we can use this in first-order reactions because the half-life is very constant. It doesn't depend on how much stuff is there. Radioactive decay processes are first order with very steady kinetics, and so we use half-life processes to figure out how old something is. So I hope that was helpful, and if not, come to class with some questions, and hopefully that gives you at least a place to start on doing your homework. All right, thanks. We'll see you.